So question 4 is very similar to question 1. In question 1 we were given the number of molecules of our polymer. This time instead we've just been given the concentrations of our polymer in solution. So if we look at polymer X, we have here that its RMM is 10,000 grams per mole and its concentration is 3.0 grams per decimeter cubed. So essentially what we want to do here is convert this value into a number of molecules. So if we start off by assuming that all of our polymers are present in just 1 decimeter of solution, we can eliminate this part of the unit. So essentially we have 3.0 grams of our polymer, and if we look to the side here, remember that moles of any substance is equal to the mass of that substance divided by the relative molecular mass. So for us that would be here, it would be moles X equal to 3.0 grams divided by 10,000 grams per mole. What this would do would be to give us the moles, and then we know that the moles times Avogadro's number is 6.023 times 10 to the 23 will give us the number of molecules. As Avogadro's number is the number of molecules or particles in a mole of substance. So if we look again at this, we see that our grams cancel out, giving our number of moles to be 3.0 times 10, divided by 10,000, and this would be to get our number of molecules multiplied by Na. And it's tempting to immediately go to the calculator and work out this figure, but for this question it's best if we wait just to see if, when we collect all our terms, to see if anything might cancel out. So if we instead go straight to the question, we know that for the number average we use the following equation: m bar n is equal to the sum of ni times mi over the sum of ni. So if we substitute in our values, we get 3 over 10,000 Na times by 10,000, and that is in addition to 5. This is the mass of polymer Y we have over the RMM of it, which is 15,000 times by Na again, multiplied by the RMM, 15,000, and then added to 15 over 25,000. This is for polymer Z, Na, and that's multiplied by 25,000. So this will all be over our Ni values, which would be 3 over 10,000 Na plus 5 over 15,000 Na, just to avoid confusion, plus 15 over 25,000 multiplied by Na. So if we look at this, more closely, we see the Ni-Mi term. This part here is relating to the Ni, and this part here is the Mi. So essentially it's the same as the first question, just slightly more complicated. So if we move on from that, we can talk about the cancellations I was saying earlier. So we could have used the calculator just to go through this. We would have left with a horrible decimal, and we could have used it again, and it just would have made all the workings look a lot messier, and it would have made the calculation slightly harder. So here we can see that if we apply what we applied to an earlier question, where you essentially look at your integer and view it as an equation over a number over 1, we can cancel 10,000s out, as it's just 10,000. It's essentially 3 times 1 over 10,000 times 10,000 over 1. These will cancel out, and we can do this for all. So we are left with a much cleaner equation. We can't do this for this part, so we'll have to just add these fractions together. So we are left with 3Na plus 5Na plus 15Na, and this is all over 37 over 30,000 Na. When working out this bottom fraction, I definitely suggest using a calculator. If you look at just the standard Casio scientific calculator, this button here will let you input fractions, so you can actually put in these relatively easily and add them together. You can do it by hand. It involves finding a common denominator between these fractions, which would be 150,000, and so you would times whatever you would need to times 25,000 by to get to 150,000, you would times the top by as well, and so you would have a bunch of different numbers over a common denominator which can then be added together, which would simplify down to the same thing. So if we move on, we see that this is 23 Na over 37 over 30,000 Na. The Na's same on the top and the bottom, so we'll cancel out, leaving us with 23 over 37 over 30,000. This being in a bracket to simplify a bit, and that will give us a number average molecular weight of 18,649 grams per mole. So the next part of this question is working out the molecular weight, and that, as we know from before, is MW being equal to the sum of Ni Mi squared over the sum of Ni Mi. And if you remember from question 1, this denominator will be the same as the numerator we just calculated, 23 Na. So if we write this out, we have MW equal to 3 over 10,000 Na times 10,000 squared plus 5 over 15,000 Na times 15,000 squared plus 15 over 25,000 Na times 25,000 squared, and that will be all over what we calculated before, which was 23 Na. Again, for further practice, you could maybe just put those in again, just practice using the sum of Ni, Mi, or just writing it out fully, but to save time I'll write it out like this. And from here we can cancel again, so instead of the whole term cancelling we have a square here, so we would remove the 10,000 from the bottom and cancel the square on top. Do this for each one, and essentially we would have 15 here times by 25,000 times by Na, and that would give us 30,000 Na for the first term plus 75,000 Na for the second plus 375,000 Na for the third, and this will be all over 23 Na. So collecting this together, again the Na's cancel out, and we are left with Nw being equal to 485,000 over 23, and that is equal to 21,086 grams per mole minus 1. So the last part of this question is calculating the polydispersity. And essentially what this is just a measure of the distribution of molecular mass in a given polymer sample. So the PDI is calculated using the following equation. It is equal to the number average molecular weight, the weight average, divided by the number average. So for ours, we get the PDI to equal 21,086 grams per mole over 18,649 grams per mole. So we know that the units will cancel out, so this value has no units, and it is equal to 1.13. So if you feel comfortable with that question now, please move on to the next.